We present MeshPose, a method to estimate a 3D body mesh from an RGB image. Our system computes the coordinates of the 3D mesh in real time, over 100 FPS on a mobile device. It is designed in a way that the 3D mesh projects well on the image. MeshPose is a human mesh recovery system, or HMR. HMR systems usually employ neural networks and statistical models that describe the geometry and movement of the human body. We start by showing that previous works, while being state-of-the-art in HMR benchmarks, do not provide image-aligned meshes. We introduce MeshPose, a method designed to bridge the gap between DensePose and human mesh recovery. Our method inherits the alignment quality of DensePose, covering the observed 2D pose and the shape of the person. We will now describe how MeshPose extracts a 3D human mesh. After processing the image with a CNN encoder, MeshPose splits computation in two parallel branches. The lower branch uses heat maps to ground the visible mesh vertices to their 2D image coordinates. This branch provides effectively the same 2D reprojection accuracy as the DensePose system, but in a vertex-based format that is useful for 3D mesh recovery. We therefore call it VertexPose. The upper branch uses global features to regress all the remaining mesh information, including the positions of the occluded or out-of-frame vertices, the relative depth of each vertex and the vertex visibilities. The outputs of the branches are merged to produce the final MeshPose prediction. Now let us focus on the VertexPose branch. The central structure of this branch is a tensor providing one heat map per mesh vertex. This tensor serves a dual purpose. Firstly, it provides the 2D coordinates of the visible mesh vertices by using the soft argmax operation. This is how this tensor operates during inference. Secondly, we can combine the scores of multiple vertices at any image position xy to predict the mesh UV coordinates associated with it. This is how we use this tensor during learning to exploit the DensePose supervision. To do this, we form a distribution over vertex activations by sampling the VertexPose tensor at position xy. We then select the three largest activations that form a mesh triangle. By normalizing the activations, we treat them as barycentric coordinates and use them to identify the pixel's UV coordinates. We introduce a new barycentric loss which aligns VertexPose channels to the UV annotations by matching their barycentric coordinates. By using this loss, alongside with two more novel geometric losses, we are able to supervise the VertexPose tensor using the DensePose ground truth signal. We showed that with our approach, we can decode both the 2D coordinates of the mesh and the continuous UV coordinates for each pixel of the input, from the same tensor. We trained with the DensePose COCO dataset and we compared it to the original DensePose method to show that it can model UV as accurately. With the VertexPose branch, we can predict the 2D coordinates of the mesh with high-quality image alignment. To get the full mesh, we also need the truncated, or out-of-crop and occluded part of the mesh. We also need to predict the depth of each vertex. The regression branch computes the rest of the 3D mesh. We use global features to compute the non-observed parts of the mesh and their relative depth. The global features are processed by a smaller, one-dimensional convolutional neural network and outputs a direct estimate of all the vertex coordinates. It also outputs a visibility vector, W. Finally, the 2D coordinates of the VertexPose branch and the full 3D coordinates of the regression branch are fused according to the predicted visibility. We train the system with a mixture of 2D and 3D datasets, plus the DensePose COCO dataset for UV supervision. We apply 3D mesh losses to the output mesh, and our UV loss to the VertexPose tensor. Additionally, we train the visibility tensor with a binary cross-entropy loss and silhouette losses. 3 MeshPose variants with different backbones were trained. For the first time, we measure the 2D image alignment of HMR with the DensePose benchmark, showing that our system is 50% more accurate than other state-of-the-art systems. At the same time, the 3D pose metrics are comparable to the rest of the systems. Our architecture consists of only standard convolutional neural network layers. As a result, the number of parameters is low and inference on GPUs is faster than other HMR systems. We have also exported our models on an iPhone 12, obtaining real-time performance. Qualitatively, the pose of the mesh is consistently more aligned to the silhouette of the person. Furthermore, It captures the shape of the person more faithfully to recover different body shapes, including children. A key property of the design of our system is that it can assign a visibility score to every vertex. This visibility score, combined with the rest of the regression branch output, enables us to handle cases with occlusion and truncation effectively. In this work we have introduced MeshPose, a system that bridges the DensePose and HMR problems and substantially improves the image reprojection accuracy of HMR. Additionally, our system is lightweight and fast, making it a natural fit for mobile AR applications, such as virtual try-on and visual effects.